Okay, hi everyone. Today I will cover two topics. The first one is about hot gas in X-ray emission, and the second one will be about black holes. Okay, so two topics. Hot gas in X-ray and black holes. Okay, so the first one should be more related to your homework, and the second one is, well, just I think it would be interesting to most people. Okay, so let's start. So for the first part, we will calculate the hot gas, the virial temperature and the hot gas in X-ray virial temperature. Okay, so let's assume that the gas atoms in the galaxy clusters and the intergalactic medium have average random speed of sigma r in the radial direction. And we also know that the average energy for each particle is 3/2 kT, right, per particle. Okay, so now let's consider only the ionized hydrogen, which is the most dominant component. Okay, so this means that we only consider a proton and an electron for each atom. And then we know that the atom's kinetic energy can be represented as 3/2 the proton mass times sigma r squared. So it should be the mass of proton and electron, but we know the proton mass is dominant. Okay, and let's say this kinetic energy is equally distributed to proton and electrons. So if it's equally distributed, then we will have the kinetic energy for proton is 3/4 proton mass times sigma r squared, right? And then if we set this, set the energy, the average energy per particle, which is 3/2 kT, if we set this energy equal to the kinetic energy, then we will get this equation. And then by canceling out, we will get the temperature, the virial temperature equals mp sigma r squared over 2k. So in this case, we call this temperature the virial temperature. Okay, and so if you'll notice that this virial temperature is proportional to sigma r squared. Okay, so now let's discuss a very general case where the radial velocity is about 300 kilometers per second in the cluster, which is 3 × 10⁵ meter per second if we want to convert to SI unit. Then we can easily calculate the virial temperature of this cluster by just plugging in the equations. So we'll get the virial temperature equals, the proton mass is 1.67 × 10⁻⁻27, and sigma r is 3 × 10⁵ squared. And we'll divide this by 2 times the Boltzmann constant, 1.38. Okay, So if you calculate this, you will get the virial temperature of this cluster as about 5 times 10 to the 6th Kelvin. Okay. So this is the virial temperature. And if you recall from the lecture, you may remember that for the hot gas in the galaxy clusters, we will have temperature approximately the virial temperature. Like the temperature will be approximately the same as the virial temperature. So hot gas in galaxy clusters. We have temperature roughly the same as the virial temperature, which means it is proportional to sigma squared. And also there's a plot, you may have seen a plot from the lecture that there's an empirical relation between the X-ray luminosity and the X-ray temperature. So X-ray luminosity and X-ray temperature. So there's an empirical relation like this, and we have many samples of galaxy clusters here, and a fewer sample down here because it's fainter. So basically, this group of samples tells us that these represents the massive clusters, because we know that massive clusters are more luminous in X-ray emissions. Okay, so for the next steps, we will show that if we take this temperature here as if we take the temperature as the virial temperature, then we can show that we can kind of recover this kind of relation between X-ray luminosity and the temperature. So, okay, so to do the virial temperature, of course, we need virial theorem. So let me write down the virial theorem. So it's 2 times the kinetic energy equal to the negative gravitational potential energy, which is gm squared over 2 eta r. And for simplicity, we'll just take eta approximately 1. So okay, so with this virial equation, we can see that basically the mass, so we can cancel out one of the mass. So we can basically see that the mass is proportional to sigma squared times r. I believe you're already familiar with this. And also, if we consider that the mass is also proportional to, let's assume average density for this cluster. So the mass is proportional to density times the volume, right? And the volume is r cubed. So if we assume an average energy, average density, sorry, not energy. So if this is constant, then we can ignore it for now. Okay, so with these 2 relations, we can basically see that, because we can cancel out 1r from these 2 equations. And so we can see that sigma squared is proportional to r squared, right? And that means r is proportional to sigma. And from the virial temperature we got before, we know that sigma is proportional to square root of T, right? So we have R proportional to sigma and proportional to square root of T, which the T here is the virial temperature. Okay, so now we get R proportional to square root of T. Okay, so this tells us that, okay, we already have the mass proportional to sigma squared times R. And we know that sigma squared is proportional to T, right? So the X-ray temperature. And then R is proportional to square root of T. So here we have square root of T. And that gives us T to the 3/2. Okay, so now we have a relation that the mass is proportional to T to the 3/2. So basically, the plot above here shows the relation between luminosity and temperature, not mass and temperature, right? But we know that mass is basically proportional to luminosity to some order, right? And so this means that we have luminosity equal to Tx to some order, right? And from, I believe, from the homework last week, you know that the exponent relation here will turn to a linear relation in log-log plot. So let's just assume this is gamma, the exponent is gamma, then we will get log L proportional to gamma times log T, right? So the exponent will turn to the slope in the log-log plot. So that this can explain a linear relation between log Lx and log Tx. Okay. So, yep, this is the first part. Any questions about this part before I move on? All right.
I have one quick question. Yeah. What is L to the beta? Is that just like some unknown power that we don't know, or some type of exponent that we don't know?
Yeah, so if you recall from the first or second homework, like you actually use this relation that the mass is proportional to luminosity to some order. And remember that you change this beta to different numbers and see how different parameters varies. So this beta is not a fixed number. It's not like we have a strong empirical relation that the mass is like L to several order. It may varies in different objects, but generally the galaxy or galaxy clusters have this kind of relation, but beta itself may vary.
Okay, yeah. Does that vary with like the overall like density or the geometry of the object?
You mean
does that beta vary with the geometry or like the density of the object?
It varies more with like it varies with both geometry and density. Yeah.
Okay, yeah, that makes sense now. Thank you.
Okay, any questions? All right, so I'll move on to the second part, which is black holes. Okay, so we know that for every black hole, we can determine its Schwarzschild radius. So the Schwarzschild geometry is the most simple model for a black hole. Schwarzschild, I'm not sure if I'm spelling this right. The Schwarzschild radius, R. Okay, so this Schwarzschild radius is defined as, because we know the boundary of the black hole is supposed to, it means that you need to have a velocity higher than speed of light to escape the event horizon of the black hole, right? So the Schwarzschild radius is defined as the radius where the escape velocity is equal to the speed of light. So to calculate the escape velocity, we can just use a very simple the Newtonian mechanics, that the kinetic energy, when the kinetic energy is equal to the gravitational potential energy, then we can get the velocity, escape velocity, as 2gm, square root of 2gm over r squared. Okay, so if we want to get the Schwarzschild radius, then it means we need to have c equal to square root of 2gm over the Schwarzschild radius squared, right? So this will give us the relation of Schwarzschild radius. It is, we can approximate it as 2gm over c squared. Okay. All right, so so it means that with a mass of a black hole, then we can determine its Schwarzschild radius with such a simple way. So for example, we know the Earth has a mass of about 6 times 10 to the 24th kilograms. Okay, so let's calculate what the Schwarzschild radius will be if we want to compress the Earth into a black hole. Okay, so if we want to compress to black hole, then, so we simply need to plug in this mass into that equation. So it's 2 times g is 6.67 times 10 to the minus 11 and multiply by the Earth mass and divided by c squared. Okay, so if you calculate this, then you will get a Schwarzschild radius of 9 times 10 to the minus third. And remember, we are doing this in SI unit, so the unit should be meter here. And this number is approximately just 1 centimeter, right? So this is a kind of a very useful analogy to, like, if someone asks you how dense is a black hole, then you can say, like, it's like compressing the mass of the Earth into a radius of 1 centimeter. Okay, so for Earth mass, the black hole should be constrained to 1 centimeter in radius. Okay, so there's also some other useful analogy for different objects. For example, for a neutron star, if you calculate that, then you'll know that to reproduce to the density of a neutron star is like compressing the Earth to a radius of about 1 kilometer. And then for white dwarf, it's like compressing Earth mass into 100 kilometer. Yeah. So I'm mentioning this just because these are all very commonly used analogy to help get a sense of how dense these compact astronomical objects are. Okay. Okay. So any questions so far? I guess this is pretty straightforward. So the next part, we will talk about the supermassive black hole in our Milky Way center. So after defining the Schwarzschild radius, we can calculate the Schwarzschild radius of the supermassive black hole. Okay, in Milky Way center. So what is the Schwarzschild radius of our supermassive black hole? So we already know that the mass of our supermassive black hole is about 4 million solar mass. So 4 times 10 to the 6 solar mass. So this is determined by the stellar object that is very close to the center, the Sagittarius A stars, and they can determine the mass by calculating the kinematics of those very close stellar objects, and by observing their change of orbits. Okay, so it's simple to get the Schwarzschild radius, just again by plugging in all these numbers, 2G, M. So M is now in, so we should convert this M into SI unit. So 1 solar mass is 2 times 10 to the 30 kilograms, and then divided by C squared. Okay, so again, if you calculate this, you will get something at the order of 10 to the 10th in meter. And this is also 10 to the 7th in kilometer. So we'll convert this unit to astronomical unit. So we know that the Sun-Earth distance is 1.5 times 10 to the 8th kilometer. So this is basically, to convert to AU, we just divide by this number. Okay, so this is the Sun-Earth distance in kilometer per second. No, in kilometer, sorry. In kilometer, and then we will get a number of 0.067 in AU. Okay, so, all right, so this means that I believe you all know that we already directly observed the supermassive black hole at the center of M87, right, by the Event Horizon Telescope. And so the supermassive black hole in our Milky Way center is also one of the main targets for Event Horizon Telescope, but it's just that since we're observing through our galactic plane, it might be more difficult to get a clear image like we see in M87, because there are more, like there are many dust along the galactic plane to interfere the observations. But by calculating the Schwarzschild radius of our supermassive black hole, we know that we need to at least receive a resolution that gives about 0.07 AU to resolve the black hole at the galactic center. So this means that, oh, okay, so let's calculate the required resolution, like in angular resolution. So since we are observing from Earth, we're observing from Earth to our galactic center. So we know the distance is about 8 kiloparsec, right? This is where the radius where the solar system is in the Milky Way. And remember, a very useful relation I mentioned a lot is that for any object in a distance of d parsec, then 1 arcsecond would correspond to d AU. So since now we're observing from 8 kiloparsec, so that's 8,000 parsec, right? Then we can easily know that 1 arcsecond corresponds to 8,000 AU. Okay, so now we can quickly calculate the resolution required. Okay, so we are observing a black hole. So this object would be the black hole at galactic center. And we know the physical size of this, to resolve this black hole would be the minimum, the minimum resolution required would be 2 times the Sloshing radius, right? And we already got the Sloshing radius, so that's 0.067 times 2. And so that is approximately 0.1 AU, right? We need to achieve an angular resolution that corresponds to 0.1 AU in physical scale. So since we already know that 1 arcsecond is now 8,000 AU, so, and we want 0.1 AU, so we multiply by 0.1 over 8,000, then we will get 1.25 times 10 to the minus 5 arcsecond. And that is about 12.5 micro arcsecond. All right, so now we know the resolution we need to observe the supermassive black hole. And as I mentioned, the black hole is observed by the Event Horizon Telescope, right? So let's determine the resolution of Event Horizon Telescope to see if it's enough to resolve this object. It's called EHT. And so the Event Horizon Telescope is observed in the radio wavelength, which is in millimeter or sub-millimeter wave. So let's just approximate the wavelength as 1 millimeter. So that is 10 to the minus third in SI unit. Okay, and so to determine the resolution, we know for a single dish telescope, the resolution is the wavelength lambda divided by the dish size, right? The diameter of the dish. And we know that Event Horizon Telescope is actually not a single telescope. It is radio interferometer with antennas everywhere around the Earth. So, we should replace the dish size to the maximum baseline between 2 antennas. So we will need the maximum baseline. And since Event Horizon Telescope is just all over the world, so the maximum baseline we can get is approximately the Earth diameter. So we know the Earth's diameter is, so the radius is 6,400 kilometer. So the radius would be multiplied by 2, and that would be 10 to the 4th kilometer, or 10 to the 7th meter in SI unit. Okay, so to determine the angular resolution of EHT, the theta, the angular resolution, is lambda over maximum baseline. And that is, so we know, we approximate the wavelength as 10 to the minus third. And then the baseline is 10 to the 7th. Okay, so then we will get an angular resolution of 10 to the minus 10. And remember the unit is in radian. Okay, so to convert radian into arcsecond, again, we can use the magic number I mentioned before. It's pretty worth memorizing, 206265. And then, so we can easily get the number of 2 times 10 to the minus 5th, and that is approximately 20 microarcseconds. Okay, so yep, this is the approximate resolution of the Event Horizon Telescope by using very simple approximations. So we can compare that. So we just calculate that we need about 12.5 microarcsecond to resolve our supermassive black hole. And then we see that the angular resolution of Event Horizon Telescope is very similar to that resolution we required. But the fact is that for the Event Horizon Telescope project, they also use some signal processing techniques and an imaging approach to even further improve the final resolution we can achieve. So we can, so although we approximate angular resolution of 20 microarcsecond, but with those techniques, we can even achieve a better resolution. Okay. So yeah, that's all I want to cover for the problem session today. Any questions?
I had a question regarding the homework, but if anyone had questions regarding the problem session, I'll let them ask it.
Okay. So any questions about the problem session first?
No, I think I'm
Okay.
good for now.
Okay, if no, then let me turn off the screen share.